So it turns out when water is moving, it can have a force. I know, that's a joke. So let's go back to Newton's. Second law, force is equal to mass times acceleration. This time we're going to go with Eulerian form and Reynolds transport theorem, so we use a control volume. So that means that the equation is rearranged to look more fluidsy like this. The sum of forces is the derivative of mass times the velocity relative to the internal reference. So that's of the systems. There's our control volume over time. Using the control volume approach, we first want to select a control volume. We do that by exposing the forces of interest. Forces of no interest should be left internal, and inlet and outlet flows should remain normal to the control volume's surface. So once we've selected our control volume, we need to talk about the forces acting on the control volume. Those are going to be the body forces plus the surface forces. The body force is gravity. So that's going to be the specific weight of the fluid times that control volume. For the surface forces, we're going to have pressure, which to make that a force, we're going to multiply pressure over the area. Specifically, if we have a pipe section, then that force is going to be the average pressure over that cross-sectional area. If we have an open jet, then our force is going to equal to 0. And if we have an open channel, our force is going to equal the specific weight of the fluid times the depth of the channel and the cross-sectional area of the channel. Surface forces can also be viscous forces. And that's going to be our shear stress acting over that surface area. And last, we can have external forces like wedges, vanes of a turbine or a fan, cables or any structural components, so on and so forth. We are talking about moving liquid, so let's talk about the conservation of momentum and adding it into the Eulerian Reynolds transport theorem. So we already have our forces due to the control volume situation, and we're going to subtract the rate that the momentum enters and add the rate the momentum exits. So we have our change in momentum that we discussed earlier, minus the incoming plus the outgoing. So we have a total sum of all external forces of this moving control volume situation. When the flow is uniform and we're assuming an average velocity, then our accumulation or some of the forces are just going to be incoming and outgoing. This term right here will be unnecessary. So with this uniform flow approach, we're going to have this average velocity coming in here, 1, so we'll call U entrance 1, and exiting here, velocity 2. And remember that the conservation of mass, or the mass flow rate, is equal to the density times flow, or the density times velocity times area. So that means that our force equation up here can simplify and reduce to mass flow rate 2 velocity 2 minus mass flow rate incoming velocity 1. Okay, because up here, remember that the incoming is subtracted, the outgoing is added. So I just switched it there so I wouldn't start with a negative sign. With this uniform flow approach, if we're assuming an incompressible liquid, that means rho is constant. That's going to be the same for M1 and M2. So the sum of our forces will be the mass flow rate, rho Q, which is constant between 1 and 2. So the only thing that's going to change are those two velocities, V2 and V1. So we are given this nozzle that's at the end of a pipeline where water is flowing at a rate of 0.0126 meters cubed per second. The nozzle is horizontal, so that means that the elevation is coming out of the page. This is laying flat on the ground, if you will, and curves at a 60-degree angle. The upstream end of the nozzle has a pressure of 46.9 kilonewtons per meter cubed. Find the magnitude and direction of the force required to hold the nozzle in place. We can see in our given image that the nozzle portion of the pipe is 60 degrees from the incoming line of the pipe. The incoming diameter is 8 centimeters and the outgoing jet diameter is 4 centimeters. I'm going to start with my control volume. So we have here our control volume diagram. Now there's forces holding it into place. I'm going to stick with our sign convention, so there's going to be some sort of force Y and some sort of force X holding this into place. Now we know the fluid is moving, otherwise it wouldn't have a jet, so we're going to have some sort of entrance momentum, rho Q V1, and we're going to have some sort of exit momentum, rho Q V2. We are assuming that this is water, so it is an incompressible fluid, so flow in equals flow out, and the density is going to remain the same. So they're not getting subscripts. We are also going to have our forces. So back here for our forces that act on a control volume, we're dealing with a pipe section and an open jet. So our pipe section, force 1 is going to be pressure 1 acting over that area 1, and the force acting back on the control volume, force 2, is an open jet, so it's equal to 0. I need to calculate my incoming and outgoing velocities. So velocity is equal to flow divided by area. So velocity 1 is going to be my flow rate of 0.0126 meters cubed per second all over that area, which is pi over 4 times the diameter squared, and my velocity 1 is incoming at 2.51 meters per second. Same thing for velocity 2 with our different area. And my velocity 2 is much faster at 10.03 meters per second. So I have my two velocities. So we need to put this all together. Okay, so we have our equation, which is the sum of the forces is equal to rho Q V2 minus V1. And in this case, we have forces in the X direction and the Y direction. So I'm going to break up those components. So I'm going to start with forces in the Y direction. So we have our reactionary force Y that I've got drawn down, so it's going to be subtracted, plus force 1, which is the pressure times the area. So that is the given 46.9 kilopascals times the incoming area, pi over 4 times 0.08 meters squared. And then I do not have any outgoing force in the y direction because it's an open jet and force is equal to 0. So that's going to equal to the density of my water, which is 1,000 kilograms per meter cubed, times the given flow rate, 0.0126 meters cubed per second, times the outgoing velocity, v2. So I need the y component of the outgoing velocity. Remember, it's 60 degrees from the vertical, so that's going to be cosine of 60. So that's v2, 10.03 meters per second, cosine of 60 degrees minus v1, which is 2.51 meters per second. We are talking about a moving control volume, so things are not equaling to 0. The forces are equal to the momentum, okay? So no equaling 0 here. A kilopascal is 1,000 newtons per meter squared. So throw in that conversion. Everything else is going to be meters and seconds and kilograms. So we can solve for force Y to equal 204 newtons. And I got a positive answer, which means my assumed direction is correct and it is acting down against the nozzle. Do the same thing for the X direction. I have force X. My incoming force pressure for that pipe is all vertical, so I don't have anything in the X direction. And it's still an open jet for force 2, so that's still equal to 0. So now I can move to the second half. Rho, 1,000 kilograms per meter cubed, times the flow rate, meters cubed per second, times the velocity outgoing, 10.03 meters per second sine of 60 degrees, minus the incoming velocity, which is acting purely in the y direction, so that velocity component is 0. And we find that our force X ends up being a positive 109.4 newtons, which means it is acting to the right, which was my assumed direction. So having those two directional forces, we can now solve for the resultant force. It's going to be the square root of the sum of the squares, 204 squared plus 109.4 squared. And we have a required resultant force of 231 newtons in 3 significant digits. So the next question is, in which direction is it acting? So if we have force Y acting down and force X acting to the right, then our resultant force is going to be acting at angle alpha, if you will. Force Y, force X, force resultant. So our angle alpha is going to be the inverse tangent of opposite force Y, 204 newtons, divided by adjacent force X, 109.4 newtons. And we solve for that value to be 61.9 degrees. So our force resultant is going to be acting down and to the right at 61.9 degrees. This time, let's say we have a boat and it is tethered to a dock in still waters, and it's shooting a water pressure cannon at 30 degrees from the vertical, and the water is coming out at an initial 3-inch diameter and an initial speed of 70 miles an hour. Find the tension in the cable that is holding the boat to the dock. Our solution is going to begin with the control volume diagram. I have the water moving out of the cannon, rho QV. and it is acting at 30 degrees from the vertical. And that's the only moving thing I have because we have calm waters. So that means my forces are going to be the tension in the cable. It's going to be the pressure force acting back on the water. And then whatever force is holding up our boat. The only thing that I'm looking for this answer is the tension in the cable. So I'm going to sum for forces in the x direction. And we are going to have the tension in the cable that's acting right, minus that force of the water, but this is an open jet. So that means that this is equal to 0 open jet. The buoyancy force is acting vertical. So you are going to equal to the density of the water, 1.94 slugs per feet cubed, times the flow rate. I wasn't given the flow rate, but I was given the velocity. So that's going to be 70 miles per hour. Oh, let's do a conversion. That's going to be a big conversion. So I'm going to scoot it down here. 70 miles per hour. And let's see, in 1 hour, we have 3,600 seconds. And in 1 mile, we have 5,280 feet. This is our velocity calculation. So in units that we want to use, I have 102.7 feet per second for my velocity. So let's plug that in there, 102.7 feet per second. And to get a flow, I need an area. So the outcoming of the jet is going to be times that outgoing velocity, 102.7 feet per second. But I only want the horizontal component, so that is going to be the sine of 30 degrees. In this control volume, we do not have an incoming velocity, only an outgoing. So that's all that's going to show up in our equation here is the outgoing velocity. Solving for the tension in the cable, we get 502 pounds. This time we're given a spillway, so that's this brown bump in the middle here, that takes our fluid acting at a 5-meter depth, speed of velocity 1, down to a 2-meter depth with a velocity of v2. We want to find the force between the spillway and the water. My control volume diagram is going to be the water just before and just after the spillway. So we have the moving water coming in, rho QV, and we have the moving water coming out, rho QV2. And this is considered an incompressible fluid, so flow in equals flow out. So I just have 1 Q, and density in equals density out, so I just have 1 rho. Now I'm also going to have my forces. So I have my open channel force here, force 1. I have my open channel force here, force 2. And then I have the force of the spillway onto the fluid, force 3. Remember the force on a spillway, force 1 and force 2, are going to equal gamma HCA. So into our momentum equation we go. Okay, summing our forces. Force 1 is the pressure due to the water before it hits the spillway, so that's going to be gamma 9,810 newtons per meter cubed, times HC, that's depth to the center of that cross section, so that's going to be 5 meters divided by 2, times area, which is 5 meters, times the depth into the page that we don't know. That's heading to the right. Force 2 is going to the left, so I'm going to subtract it. Same specific weight, 910 newtons per meter cubed. The center to its cross-section, 2 meters divided by 2. And its area, 2 meters times depth that we don't know, minus force 3. And this needs to equal to the density of water, 1,000 kilograms per meter cubed, times the flow rate of the water. I don't know the flow rate, but this is an incompressible fluid. So flow in equals flow out. So I just have to pick one side. Flow is equal to VA. So I'm going to say this is V2 times area, 2 meters times depth. And then it is flow velocity out minus velocity in. So it's going to be V2 minus V1. All right, I have a lot of unknowns in this equation, so let's clean it up a little bit. All of our units are in newtons, meters, kilograms, and seconds, so I'm just going to leave that. And I've combined all my constants to get 103,005D minus F3 is equal to 2,000 V2D times the difference V2, V1. All right, I can get a relationship between V2 and V1 using continuity. Flow in is equal to flow out. So V1A1 is equal to V2A2. So our velocity 1 times the area 1, 5 meters times D, is equal to velocity 2 times area 2, 2 meters times D. And solving for V1, I get it to equal 2/5 of V2. So now we've got a relationship between those two, but I still don't know what the velocity is. So we can use the energy equation. Using my same points where 1 is before the spillway and 2 is after the spillway, our pressures are going to go to 0 because they're both open to the atmosphere. I do not have a pump, I do not have a turbine, and I don't have any head loss. I can take the V1 that I just solved for here and plug it into this energy equation, and what I'm going to have now is elevation 1, 5 meters, plus V1, so that is 2/5 of V2 quantity squared over 2 times gravity is equal to Z2, 2 meters, plus V2 squared all over 2 times gravity. And by the way, I just set up the datum to be at the bed of the spillway. So the elevation of the before the spillway and the elevation after the spillway are my Z elevations. Solving for V2, I get a positive negative 8.371 meters per second. Plugging that back into my relationship with continuity, and I have V1 is equal to 3.348 meters per second. I'm just using the positive value because we don't want a negative velocity. All right, I have V2 and V1. I still don't have depth into the page. That's okay. 103,005D minus F3 is equal to 2,000 V2 8.371 D times 8.371 minus 3.348. Now that I have my velocities plugged into my momentum equation, I have negative force 3 is equal to negative 18,909 times D. So my negatives are going to divide out. Force 3 is equal to, and let's see, we're in newtons and meters, so that's going to be 18.9 kilonewtons per meter times whatever distance into the page D for our force 3. I got a positive answer, so that means the spillway is pushing on the water and the water is pushing onto the spillway. So for every 1 meter into the page, we have 18.9 kilonewtons of force. Just a reminder, the hydraulic grade line is going to be that open water surface. Since this is an open channel, then the hydraulic pressure head and the elevation head are already at the level that they want to be. And then we have the energy grade line. That is going to be the velocity head higher. So this is V1 squared over 2G, which happens to equal 0.571 meters. And then the velocity head over here, which is V2 squared over 2G, and that is equal to 3.571 meters.